Okay, hello everybody. Welcome to workshop number 3. Today we're working on energy conservation problems, and specifically we're going to take a look at LOL diagrams. So to begin, I want to do a little preparation. We're just going to write down the equations that we think will be useful to tackle energy conservation problems. If you guys already know this and you're watching the recording, maybe give it a pause and think about it before I start writing them down. Okay, so I'm assuming you had a chance to think it over. When we're talking about energy conservation problems, right, kind of in the title, we're saying that energy is conserved. It's a special type of problem where we can treat energy as being conserved. And that is to say, energy is conserved within some discrete system that we choose. Because we know that energy in the universe, or the scale of the universe, is always conserved. Energy never disappears or is suddenly created in the universe. It just kind of goes to other places. And in these energy conservation problems, we're going to consider some discrete system. It's going to include a limited number of pieces. And we're going to say the energy is conserved among those pieces. And the LOL diagram is going to help us with that. But if we just think about the core equation, the very core one to always remember is super easy. It's just E initial is equal to E final. And that comes just straight from what we're saying. Energy is conserved. So the initial energy is equal to the final energy. However much energy we started with is however much energy we have in the end. Now, as we look at our system, there may be different elements to it. And there's different forms that energy can take. And sometimes energy transforms from one way to another. Really, it's almost like an accounting trick. It's like we're keeping track of money. No money disappears, it just goes to other places. So sometimes we'll expand this out. And the way that you expand this out is going to depend on your system. But a really typical one is going to be to break this into kinetic energy. Thank you. Energy having to do with motion. So this is the initial kinetic energy, KEI. And then there may be also some potential energy. And I'm going to denote that with a U. Maybe that's a potential energy due to gravity. Maybe it's potential due to a spring, something else. We'll say gravity for this one. So let's call it UG. We'll give that a subscript I as well. And that needs to equal, in the end, the final kinetic energy. Plus the final potential energy. And again, that could be gravity, could be a different form. So for the LOL diagram, we're using the letters L, O, and L. They're not as letters. The L is a chart. The second L is another chart. And the O is just going to be a frame for whatever we're considering in our system. So I'm going to demonstrate how that works. Let's go to the second part of the worksheet. So we're going to take a look at an example of an LOL diagram. This is just going to be a generic one. So the way we do these when I start out is I just draw a big LOL. Okay. There's my L. Like I said, this is going to be a chart. Going to do a big O and another L. Okay, so the way this works is this is our final energies. This is where we're going to tabulate them. So this is E final. And this is our initial energies. This is E initial. And then whatever elements we draw inside this circle are what we're considering to be conserved. So we pick some system. Let's pick a really common example. We're going to say maybe there is a ball, some object. Okay. And there's the Earth. Here's Earth down here. Not a great drawing of the Earth, but maybe I'll write in Earth so we don't get confused. Okay, I'm going to trust you guys get the idea. I'm calling this the Earth. It's not the greatest drawing. You get the idea. So if we analyze this system initially, we can see that this ball is somewhere off the surface of the Earth. So it has a potential energy due to gravity, right? We're going to mark that underneath here. We're going to give it some potential energy. And let's say initially, and this will depend from problem to problem. You read the problem, you analyze the situation, you think about what is your initial instant, what is your final instant. So let's say initially it's just sitting in place. So the kinetic energy is there also, but it's 0. There's our element of kinetic energy. It possesses some potential energy because gravity wants to pull it down, wants to bring it to the Earth, wants to make it fall. And then we do the same thing here. And now let's consider our final instant to be right before this ball makes impact with the Earth. So maybe we kicked it up in the air. We waited until it was just starting to fall. We called that the initial instant. And then now, right as it's about to hit the ground, we call that the final instant. So now the kinetic energy is a maximum, right? It's been building up kinetic energy over the course of its fall. There we go. Actually, it's a little tall. There we go. And now the potential energy is now 0, right? Because gravity has pulled it as far as it can go, as far down as it can go, which is to the surface of the Earth. This is about as simple as you can make your little diagram. But what is always true in these little diagrams is that the summation of E final is equal to the summation of E initial. So what you can see with these diagrams is there's an exchange between types of energy. But the left-hand side, that's first left L, whatever we add up in the bar, maybe this is 4 units of potential energy, it's going to equal this side. This is 4 units of kinetic energy. This is 0. 4 and 0 makes 4. 0 and 4 makes 4. And there will always be that balance. And you can think about this conceptually, whether you draw out the diagram or not, picture it in your head and imagine how there is an exchange of energies, but no energy is lost. So the total energy in the end is equal to the same amount of energy that you began with, the total energy in the beginning. Okay, that's a quick example of the very easy version. Let's try to use this to tackle a couple of problems. All right, so we're looking there on the screen. This problem says 2 64 kilogram stick figures are performing an extreme blob jump as shown in the diagram below. It says that these are professional stunt figures and we shouldn't attempt this at home. Okay, we'll take that under advisement. One stick figure stands atop a 7-meter high platform with a 256 kilogram boulder. Okay, wow. A second stick figure stands on the partially inflated airbag known as the blob or water trampoline. The first stick figure rolls the boulder off the edge of the platform. It falls onto the blob, catapulting the second stick figure into the air. What is the maximum height that the stick figure can rise to? Assume that the stick figures, boulders, and blobs obey the law of conservation of energy, which of course they should. Okay, if we go in, okay, maybe you've seen this before. Essentially what happens is this is a partially inflated bag of air. Someone jumps from a high height or drops a large weight onto one side of the airbag. It forces all the air rapidly underneath the person who's standing over the top of the water. And that quickly launches them into the air. And that's kind of a complex scenario. There's a lot happening here. But the beauty of the conservation of energy is it allows us to skip a lot of steps. It allows us to simplify things a lot. Whenever we can assume that energy is conserved, and it tells us that we can do that in this problem. So what we know then, despite this kind of complicated situation, someone pushes a boulder falls, it stamps an airbag, the airbag pushes a person. We know that whatever the initial energy is, that's going to be equal to the final energy. And that will make things quite a bit easier for us. We'll see how that goes. So we pick some initial instant, some initial amount of energy, and then we set that equal to the final energy. And we're going to try to use that to solve this question, which is, what is the maximum height to which the second stick figure can rise? Okay. So we know that our initial energy, what is this problem, right? We do our LOL diagram. Let's see here. I'll do this off to the side. Okay. Now, as you get practice with these, you don't really need to draw out this LOL every time, but it is a good trick to help you get a handle on all of the elements in a conservation of energy problem, and help you to kind of keep track of things while you're familiarizing yourself. So what are the elements that are involved? It says that we're going to push the boulder over, right? So the boulder is going to fall. Certainly the boulder has some energy. Let's put that in our system. The reason that the boulder has energy up on the tower is because it's going to be yanked down by the earth, right? So let's put the earth back in our system. It's going to be down here. And then the other thing that's in our system is our guy, right? It's going to be launched in the air. The second stick figure, we could include him, but the instant that I want to consider, the initial energy, is right as the ball is about to fall, the boulder is about to fall. We don't really need to include him. You could if you want to. It doesn't really change anything. What are the energies that are relevant for this? There's definitely going to be some motion, right? We see there's a boulder about to fall, then there's someone going to fly in the air. So in the initial instant, right, we're going to label this part one. In the initial instant, what are the energies that are relevant? Well, the boulder is not moving yet, but it has some potential energy, right? It possesses some potential energy due to gravity, UG. And then in part two, this person, we want to know what is going to be their maximum height. So we want to know what is the top height that they're going to get to. So really, the final instant that we want to consider is when they've flown as high as they're going to get. Their kinetic energy has dropped back to zero. They went as high as they could. And then they possess some potential energy, right? Because they're going to fall back down again. You can consider different points in time, and you can try to work it out, but you have to think about what is the problem asking and how do I get there most efficiently? So here's scenario 2. So we're going to try this approach. Let's see what that gives us. So then it should be that, okay, it should be that in the end, we have a large mass, M, multiplied by G, H. This is H for the tower, okay? And that should be equal to the small mass of the stick figure, M, also multiplied by gravity, times H max, which is the maximum height that the stick figure is going to reach before he loses all his kinetic energy and starts to fall again. Now, mgh, we get that just from what is the gravitational potential energy somewhere near the surface of the Earth, mgh. And that will be true as long as you're not too far away from the surface of the Earth that the gravitational acceleration starts to change. Certainly, we can say these guys are on Earth. They're doing their trampoline jump. So we're good to use mgh. If we go from here, we see we've got gravity on both sides. So let's just drop it out of the equation. I'm dividing both sides by gravity, and gravity disappears. Okay. And then what did I want to solve for? I wanted to solve for H max. Okay. So I've got a capital M here. I've got HT. It's the height of the tower. They told us that was 7 meters. And then we divide that by the mass of the stick figure. And that should tell us H max. If we think about this equation and we check if it kind of makes sense, what we've derived here, what I'm saying is that the maximum height you reach on a blob jump depends on the height of the tower, the height from which you launch, right? I think that kind of makes sense. You get the feeling that if you jumped a really long way and gravity continued to speed you up, you would be able to launch something higher. And then it also depends on the ratio of the masses, right? So if a really large object falls, it could launch a smaller object quite a bit higher. Or if vice versa, a small object falls, it wouldn't launch a very large object very far. So that seems to work with our intuition. All that's left to do now is punch this into the calculator. So it was 256 kilograms for the boulder, and we multiply that by the 7 meters that we were off the ground. We divide that by 64 kilograms for the person, and we get a maximum launch height of 28 meters. 28 meters, which is really substantial, super substantial. This guy is flying in the air, but it was a really massive boulder that launched him, and it was a pretty significant tower that he was launched off. So yes, these guys are definitely stunt figures, and we should not try this at home. 28 meters in the air, that's in the neighborhood of what? Over 50 feet. I would not want to do that myself. But good for them. 28 meters is his max height with this setup. So you can see this would be a pretty complex problem. Maybe when you were reading it, you didn't know how to approach it at first, or maybe you're pretty familiar with these energy conservation problems, so you knew right away. But like I said, it was a complex scenario. But just due to the fact that we know energy is conserved, right? We can just set their potential energies to be equal. And we get straight away to the answer. This was really simple algebra. I just had to divide by G, and then I just had to divide both sides by M, and I was done. 2 steps. Very easy. Okay. Let's do the next one. All right. So this one says, the diagram below shows a 10,000 kilogram bus traveling on a straight road which rises and falls. The horizontal dimension has been foreshortened. The bus at point A is 26.82 meters per second. Oh, the speed of the bus, I'm sorry, 60 miles per hour. The engine has been disengaged and the bus is coasting. So there's no acceleration, that tells me. The friction and air resistance are assumed to be negligible. The numbers on the left show the altitude above sea level in meters. The letters A through F correspond to the points on the road at these altitudes. Okay, so yeah, let's break that down. That was a pretty lengthy setup to the problem. Let's make sure we understand everything they're telling us in here. So the bus is 10,000 kilograms. They give us a mass. Let's go over here. We'll write our knowns. Mass is equal to 10,000 kilograms. Okay. All right. Horizontal dimension has been foreshortened. What does that mean? It just means this diagram is not exactly to scale, at least in the horizontal direction. So the bus could be traveling a long way, maybe even a portion of a mile, as we see. So the slopes might be more gradual, may or may not be relevant. The speed of the bus is V, is equal to, this is V initial, we'll call it, since this is the velocity at point A, and it's equal to, they tell us, 26.82 meters per second. The engine is disengaged and the bus is coasting. So we're not speeding up, we're not slowing down, we're coasting. So acceleration in the X direction, at least, is equal to 0. There could be some acceleration due to gravity. We'll talk about that in a minute. Friction and air resistance are assumed to be negligible. You've probably seen this many times. It's a simplifying assumption to make the problem easier. And what it does is it removes friction and air resistance, which air resistance being essentially another form of friction. Both of these are non-conservative forces, which mean they kind of rob our system of energy. They make it so that the energy we start with is going to end up actually being less than the energy that we end up with. Because as the friction kind of, basically there's some loss of energy that becomes thermal energy. But we get to ignore that. We get to ignore that. So this is basically telling us that we can assume energy is conserved. Because now we look at the other forces, right? We see the other forces at play are gravity, which is going to be a conservative force. The numbers on the left show the altitude. So this is just telling us how to read the chart. So we can see there's different heights at these different points, as it's either climbing or going down the hill. It says find the speed of the bus at point B. So we got point B right here at the bottom. So let's think about that before we do any math. Just make a prediction. We have some initial speed and we coast downhill. So will we gain speed or lose speed? We're probably going to pick up some speed, right? Gravity is going to help us down the hill. It likes to do that, very generous. And then we're going to have an increased speed there at the bottom. That's part A, and then part B is an extortionist is planted a bomb on the bus. Okay, part B we'll do in a second. Sounds like it's getting crazy over there. Let's do part A first. So find the speed of the bus at point B. How do you want to approach it? If you're not sure yet, go to your lull diagram, right? Go to your lull diagram. You're getting the idea of it, getting the practice of it. In the circle, draw what we're considering, right? It's asking us about the bus. And we know that the bus is being pulled by gravity down the hill. So it seems like we've got the bus in here and we have the earth. I'm just going to write bus and earth. Okay. I know I'm not doing you guys any favors with my drawings, so we'll just write it out. Okay. Now, initial frame is going to be point A. So let's put this as point A. Now at point A, we have some initial velocity, right? So there's some kinetic energy. This is kinetic energy. We're also at a certain height. We're at 55 meters of height. So don't we possess a certain potential energy as well? Okay. If you want to do your chart accurately and actually kind of measure these out, you can. I just like to do it conceptually, give us the idea that these need to be equal in the end. UG, we've got some kinetic energy. Now at point B, we have some potential energy. We're still 50 meters above sea level, right? But we've lost some of it. So the potential energy has decreased. And what does that mean? If we have less potential energy, but the same amount of energy overall, then we must have more kinetic energy to make up for that deficiency in the potential energy. We must have more kinetic energy than we started with, right? So this is our kinetic energy. This is our potential energy. Okay, so this is our constant, and then this meets up with our intuition. We thought we were going to speed up. We thought we were going to go faster. It looks like, yes, we are. So let's put the math to it. What do you want to do? We say EI is equal to EF. That is, we break that into parts. We've got KE, kinetic energy, plus the potential energy is equal to KE at point B. Now, maybe you've done this several times and you just want to write out immediately, you just want to go to MGH and all that. And that's okay if you feel very comfortable with that. But I like to go through these steps, and I always like to remind myself where this is coming from. It just comes from the very simple start, the claim that the energy is conserved. And then we can kind of add to that from there. So if we do that, go ahead and expand this out. Kinetic energy is equal to 1/2 the mass that is on the move, the mass that has a velocity, times the square of the velocity of that mass. The potential energy is, as we know, it's going to be mgh. And specifically, this is the height at point A. So can I say HA? I'm going to say HA. We're going to set that equal to, and I should say this is the velocity at point A, since we know the next one will be different. This is going to be 1/2 m v squared. This is the velocity at point B, and that's going to be equal to mg h b. Okay, so if you haven't already, pause me and try to solve it on your own. Try to solve it on your own. I think you don't need me for this. Okay. Okay. I'll move down. Okay. So we're going to work through the algebra from here, right? The setting these things up is the more difficult part, or the tricky part. Now we're just doing algebra. So we want to find, what are we trying to find? What is the velocity of the bus, right? The speed of the bus. So we're going to find the velocity. They just want the speed, so we don't even need to worry about the direction in the end. But yes, we want to find VB. So we want to isolate that. The first thing I think I'm going to do is I'm going to multiply the whole equation by 2, get rid of those fractions. In which case we're going to have, okay, where'd my pen go? There we go. We're going to have m VA squared plus 2 mg HA is going to be equal to mVB squared plus 2 mg HB. Okay, now, don't we see that everything in this equation has an m? So can we just divide out by m? Red. M goes away. M goes away. So they told us the mass of the bus, but we didn't need it for this part. Maybe we'll need it later, I'm not sure. All right. Okay. We want to get VB alone. So can I do 2 moves at once, you guys, as I do this? So I want VB on its own. I'm going to say V A squared, V A squared. Okay. Now, I'm going to factor out, we've got a 2G here. And then this is going to become HA minus HB. So you see what I did there? I just subtracted both sides by 2GHB. And then I saw a common factor of 2G. And I factored that out. So what does this say? This really says the difference in height between HA and HB. And they'll work out like that quite often. Really, when we're considering, like I said, we still have some potential energy 50 meters here. But really what's relevant to the final velocity is just how much we changed. How much we changed in the potential energy, right? The change in the potential energy is what determines the final kinetic energy. And all of that we have is going to be equal to VB squared. Okay, so we take the square root of this answer right here, and we'll be all done. Let's punch that into our calculator, and let's calculate VB. Okay, you guys do it at home. Make sure I don't make any mistakes on my calculator here. Our initial speed was, I think it was 26 point something, 26.82 meters. 26.82 meters per second. We're going to square that. Then we're going to add to that, we're going to add plus 2 times 9.8. Okay. And then we're going to add, let's see. Okay. Okay. The difference in the height is 5 meters. Plug that in. the square root of the answer. I have 28.58 or 28.59 meters per second. Okay. 28.59. Compare that to 26. It looks like, yes, we've sped up a little bit as we decreased in height by about 5 meters. That seems pretty reasonable, seems to make sense. Okay, let's look at part B. An extortionist has planted a bomb on the bus. If the speed of the bus falls below 22.35 meters per second or 50 miles per hour, the bomb will explode. Oh gosh. Will the speed of the bus fall below this value and explode? If you feel the bus will explode, identify the interval in which this occurs. Okay, so they're saying, will the bus explode by going too slow? And if so, where, as it transitions from maybe B to C or C to D or D to E, perhaps, or maybe somehow E to F. Okay, so let's take a look at that. Once again, you give it a go, you think about it, and then I'll start working on it alongside you. Whenever we do these workshops, do as much of the work as you can by yourself, and then just watch me when helpful or when needed. Try to use me as little as possible, the way you do your work as much as you can. Okay. So we want to find if the bus will fall below a certain speed. So this previous work that we did here, it strikes me that we already really derived an equation for the final velocity, the velocity at some secondary point, based on an initial velocity at some point A, depending on the difference in height, the height change. So let's keep what we've done. Let's keep the velocity at A, and let's just consider the velocity at some unknown point. I'll call it Y. Okay. Okay, so here we have VA squared. We're once again adding 2g delta H. This time, the change in height is going to be from our starting point HA to some final point, which is going to be called HY. Okay. And that's going to be equal to the final velocity, which I'm going to call V at some height Y squared. And we want that to be equal to 22.35 meters per second. So we can see if the bus is going to explode. We're going to see if it ever does end up going that slow. Now let's just think about the equation that we've written here and try to make some sense of it. So what we can see is we start with HA, and then if HY is greater than HA, we'll end up with a negative number in the bracket here, in the parentheses, right? And that means that from our initial speed, we'll have to subtract this term. So the final speed will be less than the initial speed once. And that would have to be true if we were going to slow down from 26 some meters per second to 22 some meters per second. So certainly it's not at point B. We already discovered that that was higher. And it's not going to be at point C either, because point C is equal. Point C is equal. We need some height that is greater than. HA in order to actually slow the bus beyond the initial velocity that it had. So let's see here. We want to identify the interval over which this occurs. So I think the way we can do this, number C, part C says derive an equation to determine the speed of the bus at any altitude. And part B says over which interval. So let's do the interval part first. We're basically already there with B and C with what we've done here. But So let's just try some points. If they give us an interval, then we can just kind of test out some numbers. So let's see if by the time we reach point D, are we going too slow? So we'll just go in with our calculator. We're going to do the square root of 26 points. I keep forgetting what the initial velocity was. Was it 82? Yes, 82. 26.82 squared plus 2 times 9.8 times HA was 55 meters. So 55 minus 60 is going to be negative 5 meters. What will that get us? That gives me 24.9. So we've not yet exploded. So maybe we can make it up to E. Let's see if we can make it to E. We're going to do the exact same thing. We'll punch it in. Square root. VA squared is 26.82 plus 2 times 9.8 for gravity times, now we're going from HA is 55, HE is 65. 55 minus 65, we get a negative 10. That seems substantial. Okay, what are we going to get here? Uh-oh. So I get domain error, which means what I have under the square root is negative. So it looks like maybe we've fully stopped by this point. Let me check if that bears out. 26. I think I forgot to square the velocity, actually. My apologies. Punch it into the calculator again. Get a negative 10 here. Okay, so I get square root. So I have 22.87. What was our target number? It was 22.35. So it looks like we actually made it. It looks like we're going to make it over the hill. Looks like we're going to make it over the hill. So we make it to point E, then we're going to be going back downhill again. So we won't slow down anymore beyond point E. Let's just double check that. Looks good. Okay, you guys double check me at home. Make sure I punch that into my calculator correct. But it looks like the bus is safe from this extortionist. I think we're okay. If we want to derive an equation to determine the speed of the bus at any altitude, we've basically got that here, right? An equation to determine the speed at any altitude, that's like a function. That means we put in an altitude and we receive the speed of the bus. So we get v of some height h is equal to, I'm just taking this from our equation that we already wrote. It's the square root of v initial, v at point A squared, plus 2g. And then this is point A was 55 meters minus h, whatever h is. There we go. Okay. I didn't have to do any new work there. I'm just making this into a nice equation. So you can put in an h and I can tell you a v. Derive an equation. And we're done. Great. So once again, another problem pretty easily solved with the conservation of energy. You can see the power of this technique. Let's look at the next one. This is actually two of them. They're conceptual. I think they'll go pretty quickly. We'll put them in together. Let's see. All right, so we have two questions here. The first one says, now this is a conceptual question, so we won't really do any math. We're just going to think about it. We can do math if we want to, but 4 identical balls are thrown from the top of a cliff, each with the same speed. All right. The first is thrown straight up. The second is thrown at a 30-degree angle above the horizontal. The third is thrown at a 30-degree angle below the horizontal. And the fourth is thrown straight down. how do the speeds and kinetic energies of the balls compare as they strike the ground? Okay, so how do the speeds and kinetic energies compare as they strike the ground? We're up on a cliff. Whoa. There's the cliff. Here we are. We throw several balls over the cliff in different paths. One we throw straight up. It goes down eventually. Okay. One we throw horizontal, 30 degrees above the horizontal. It goes down eventually. Okay. Another one we throw 30 degrees below the horizontal, something like that. And then the very last one we threw straight down into the ground, just straight down. Okay. And the question is, when these strike the ground, how do their speeds and kinetic energies compare? You guys think about that for a minute. How do their speeds and kinetic energies compare? Okay, let's have a look at it. So we could do our LOL diagram if we want to. Let's just try and think this through from what we know, right? The first one says when air resistance is negligible. So that's giving us free rein to say that the energy is conserved. The energy is conserved. So if the energy is conserved, then the initial energy is going to equal the final energy. What is the initial energy? The initial energy is all this potential energy up here, right? We have a potential energy by virtue of us being at some height above the earth, above the ground. And then we also impart some kinetic energy by throwing the ball. And we throw all the balls at the same speed. So doesn't that mean we give them the same kinetic energy? Maybe not in the same direction, but we do provide them the same kinetic energy. And then ultimately, when they hit the ground, they've lost all of their potential energy, and all the energy in total has been converted into kinetic energy. Okay, so which one hits the hardest? The one we throw down full all our force straight into the ground, or the one we throw up? I guess let's just consider these two first. Let's compare these two, and then we'll think about the other ones. So one of them we're throwing down. We go straight into the ground, and all of our kinetic energy that we add is directed straight into the ground, and then it strikes the ground with some energy. In the other hand, when we throw it up into the air, all of our kinetic energy sends the ball, or all the kinetic energy that the ball possesses when we throw it, sends the ball higher into the air, and then it gains more potential energy. And then it has longer to fall. So it gains more kinetic energy as it falls. And which one of these hits with a faster speed, or which one of them hits with a higher kinetic energy? Well, neither. They hit with the same. We gave them both the same energy. They started with the same energy. That means they end with the same energy. One of them we threw downward. One of them we threw upward, but it doesn't matter. They have the same initial energy. In the end, they've got the same final energy. Okay. Let's think about these ones that we threw horizontally. We threw these at two different angles similarly. And it seems like we could use the same argument, right? We give them the same initial energy, no matter the direction. And they end with the same final energy, no matter the direction. And if we compare the one we threw up, the one we threw down, the one we threw side, all of these, in fact, we give them all the same energy. We throw them all at the same speed. They all have the same kinetic energy. This one right here, the one that goes up, it loses that kinetic energy, but it trades it for an equal measure of potential energy. It's an even trade. So it ends up working out that these are even. This is the same with all of them. So all four of them will hit with the same kinetic energy and speed. Now, those speeds and those kinetic energies will strike a bit differently. This one will strike at a bit of an angle, right? It's still continuing off to the right. This one the same. They have some kinetic energy that's in the x direction. So they don't just hit straight down into the ground like, say, this one does. But if we think about the total energy that the moving body possesses, those energies are equal. What about if their air resistance is significant? What if the air resistance is significant? So we haven't talked about this too much in this workshop, but we usually don't consider the air resistance, right? What does the air resistance do? It's like a friction that slows us down. It steals away some of our energy as we travel. And the amount of energy that it steals away is dependent on our velocity. So the faster we go, the more it tries to impede us, the more that it tries to resist our motion. So what would this do? It's going to start to steal out energy from each of the balls as we throw them, But the air resistance is not time dependent. It's dependent on some constant, for how thick the atmosphere is, and it's dependent on the velocity. And we gave all these guys the same velocity. They end up with the same velocity. So let me think. I'm thinking though, let's see. And it is a little bit time dependent. If we throw the ball straight down, it initially has the most velocity, so it's the most slowed. It gets the most resistance. Okay. Versus if we throw this one up into the air, it loses some energy that travels up into the air, and then eventually it stops, and then eventually it turns around, and then it continues to lose more energy. Ultimately, what this will do is it will steal out some of the energy from all of the balls. So the initial energy is going to be greater than the final energy. But still, these energies will be equal. The final, and not that the initial energy will equal the final, but that the final energy of all these different projectiles will be equal. Okay. A ball is dropped from the top of a building and reaches a terminal velocity as it falls. At terminal velocity, drag is equal to the weight falling and the object stops accelerating. Will the potential energy of the ball upon release equal the kinetic energy it has when striking the ground? Explain the reason. Okay, this is basically the same. This is a very similar question. We'll just go more into depth, which is actually great. Okay, so what was I talking about just a second ago? A little bit more in depth. So what does it mean for an object to reach terminal velocity? You've maybe heard of it before. It means it reaches the maximum speed at which something can fall. And the reason that that happens, I don't want to go too much into the math because you guys usually won't look at too much air resistance during your first 2A course. But we can think about it conceptually. What happens is, depending on your speed, as you speed through the air, you encounter all the particles that are in the air, and you kind of have to push them out of the way. You have to move them out of the way, and they resist being moved out of the way a little bit, just like when you're pushing through water or when you're swimming through water. This is a less dense fluid, the air. But especially as you pick up speed, it becomes more and more noticeable because you have to move more and more of these particles out of your way, and more of them kind of push on one another and push on you. So what happens is, as you're falling, eventually you reach an equilibrium where you reach such a speed, you accelerate to a point that the upward force from the drag is equal to the downward acceleration due to gravity. And once that happens, you've reached your maximum falling speed. Before that, you just keep falling faster and faster and faster and faster. And it doesn't stop until you reach that terminal velocity, until your drag equals out with that acceleration. So once that's happened, it says, will the potential energy of the ball be equal to the kinetic energy it has on striking the ground. Well, so let's think about that. So there's two ways we can think about it. One, we can think about how this is not a conservative force. So it tries to steal energy away from us. There's friction as all these particles are moving past. It's heating us up. It's stealing away some of our energy. So as we fall, we actually end up with less energy than we started with because the air ends up taking some of it and our clothes take some of it as they warm up, and it kind of goes in different places. So the energy ends up being less. The energy ends up being less. Okay. The ball is dropped from the top of the building. The velocity of drag stops accelerating. Will the potential energy of the ball be equal? And the other way that we can think about this is you possess some potential energy due to gravity, right? And usually what happens is all of that potential energy converts into kinetic energy. If you think about our Lowell diagram, then it's that basic one that I showed you in the beginning. It starts out with a lot of potential energy. It ends with no potential energy and all kinetic energy. But the energy is not conserved. There's a non-conservative force here. If we're not continually able to just speed up and exchange our potential energy for kinetic energy, we don't get that full conversion. Some of the potential energy turns into a different kind of energy, thermal energy. It goes elsewhere. So the kinetic energy can't be equal to the full amount of energy that we started with. We had to split up that energy among other parties. Again, and it's like I said, it's like money. We're doing accounting. We started with $100 and we wanted to give most of it to our favorite child, kinetic energy. But we can't give it all to that child. We have to split it up evenly among the family, or we have to split it up to some degree among different members of the family. Okay, so that's all for this workshop. We've talked about conservation of energy. We talked about also a little bit what happens when energy is not conserved. We just did that conceptually. We went through the math. You guys learned how to use LOL diagrams. You can utilize those. And the core equation to always remember and always stick in your head is whenever you hear conservation of energy, initial energy is equal to final energy. And then you can think about what energies are involved in your system, and you can work it out from there. You can derive it from there. Sometimes in physics, you have to remember complex equations. This is not one of those times. You just remember this. EI equals EF. And you can build up from there. You can build up from there. Energy framework is tremendously powerful. We solved some pretty complicated problems very easily, very straightforwardly with math. And you'll continue to see that throughout your 2A course. So whenever you think energy might be conserved, be tempted to look at this framework and see if you might solve the problem more easily, as opposed to using your kinematics or something else. Okay, thank you. I hope you found this informative. Give it a go, give it a practice, think of other problems, and I will see you next time. Y'all have a great day.